You have probably played a game with your friend at some point. Your friend probably asked you, there are a few given numbers. What is the pattern here? What is the next term? And if your friend is a bit more math heavy, he might also ask you, what is the sum of those first few terms? And today we're going to let you in on how mathematicians do this. And that is basically called sequences and series. Well, at first, listing out a few numbers and trying to predict the next term seems like child's play. But in fact, this leads to some of the most important parts of math, modern math and frontier math, including the Riemann zeta function. And why that is so, I will show you in a moment. So in today's video, we're basically going to focus on two things. We're going to focus on what is the sum of sequences. What is the sum of the first few terms of a sequence? This is what is a series. And then meantime, we're also going to try to predict whether a sequence blows off to infinity, keeps on moving up and down but never settling down, or it converges to some point and never goes beyond that. We'll go into more detail about these in a moment. And first, a quick note on terminology. We have already mentioned a sequence, generally written as A1, A2, dots, AN, or sometimes written simply like this. This is a sequence. We're focusing on the numbers. However, a series, we're focusing on the sum. For instance, the sum of the first k terms, this is a series. And this big sign here is called sigma. It is a capital version of sigma, a Greek letter. And this essentially represents summing up every possible term, or here this means A1 plus A2 plus dots plus AK. Well, it basically means there is an index. So the index is going from 1 up to k. This is the limiting upper bound of the index. And what we have here is the initial value of the index. Then this index moves one by one upwards. So this is the sigma sign. And you can try to prove this yourself, but there are two calculating rules for the sigma sign, or the summation sign. It is first that you can move the constant out. For instance, this, where c is a constant that is the same for every single term, this can be written as c times the sum of ai. And similarly, you can break sums, which means suppose you have two sequences. This can be simply written as I equals 1 to n of ai plus the same thing of bi. These are two calculating rules for the summation sum. And you can prove this yourself. This is not really that hard. So I will move on for now. As I mentioned, we will be trying to find series or predict the future of sequences. For instance, one might ask, what is the nth term of a sequence? And you can only represent it using n. And as for series, the problem might just ask, what is the first n terms sum? And finally, for convergence, which is also an important term, there's generally not many AMC12 problems on convergence, but this is the most crucial part for you to understand the essence of sequences, and it is where we start to sneak into advanced math. So we'll be covering these three areas one by one. First, we will focus on series, because this is the most common and simultaneously the easiest to deal with. This is the most basic possible problem for finding the sum of a sequence or the series. Well, you can take a moment and try yourself, and I am expecting you to be able to solve this. Well, in this problem, we use the technique called constant sum. Because if we want to calculate this thing, apart from brute forcing it from the first term to the last term, we want to find something special in it. And that requires a constant thing so we can actually combine certain terms together. And first, we're going to focus on the constant sum. And you might notice here that 1 plus 99 is equal to 3 plus 97 is equal to 5 plus 95, etc. So this is a constant sum. And of course, some folks also say that this is the pairing technique. But personally, I think this is a better name because this is really highlighting that you're not pairing to pair. You're pairing to find constant values, and it happens to be constant sums. In this case, we have a total of 50 pairs. In this case, we can repeat the same thing for every single number, all the way up to 99 plus 1, which is still the same 100. Since there are 50 numbers from 1 to 99, there is a total of 50 pairs times 100. And then after that, since we counted each number twice, we have to divide it by 2. So the answer here is 2500. and we're done for this problem. In general, suppose we have what is called an arithmetic sequence, which can be defined as the nth term is the last term plus a common difference d. You can rewrite this as an is equal to a0, which is the initiating term, plus n times d, because there are n such d added from the 0th term to the nth term. In general, this thing can have a clear way to calculate the answer to what is the series. So the arithmetic series formula, which is basically I equals 0 up to n, summing of ai, it is again the pairing technique, because a0 can be paired with an. The sum of these two are 2a0 plus n times d. a1 plus an minus 1 similarly is 2a0 plus nd, etc. So everything is the same. That means there are a total of m plus 1 terms, because we also counted the 0th term. And then the sum for every single one of them would be a0 plus an, or also 2a0 plus n times d, divided by 2, because we have counted twice for each number, and we're done. So this is essentially the first formula that we are going to learn in this course, the arithmetic sequence formula. And drawing on this technique, we can also assume that there is a way to change constant sum to difference, which others call canceling, or sometimes telescoping. But again, I think I'm going to go by constant difference, because this again highlights that we're chasing a constant value. Let's look at this. We're supposed to find this thing, and note that this is simply 3 to the 0th power plus 3 to the 1st power to the 2nd to, in the end, 3 to the 6th power. And we're supposed to find this thing. Well, we need a constant difference. And in this case, since you don't have much experience, I'm going to tell you the constant difference should be 0. That is when canceling happens. How? You can experiment around a bit by yourself. So the way to go here is, suppose this value is s, then 3s would be this, because everything is going to be multiplied by 3, so the exponent is going to be added by 1. Then we gain a constant difference of 0 in every row. If we focus on them in every row, all of these have a difference of 0. Then that means 3s minus s would then be equal to 3 to the 7th power minus 1. Or this can also be written as 2s. So s is equal to 3 to the 7th power minus 1 divided by 2. And this happens. So of course, this thing can also be simplified further, but this is a huge exponent, so we're not going to calculate it exactly. But at least you know how to calculate it now. Well, in general, we also have the geometric sequence, where it can be defined by an is equal to the last term multiplied by a common ratio r. Or in general, an is also equal to a0 times r to the nth power. This is similar to the arithmetic sequence. Then we have the series formula, which essentially is just summing an, which, as we know, we have a constant multiple of an. So we can first bring out the a0, and that means we're actually looking for a0 times r to the ith power. That means, so this is a 0 here, a bit unclear. And the formula is simply and that is our formula, a0 times rn plus 1 minus 1 divided by r minus 1. The second formula in this course. Now, of course, you don't really have to remember this. The reason of which is because, firstly, it is really easy to derive. So whenever you forget, you will remember that you're going to use the constant difference. So then you can arrive at the same result yourself easily. The second thing actually is that when you use it a lot, you just naturally remember them. So I have never tried to remember this formula myself, but by now I can just recite it by heart. Now, we will be analyzing a problem next that is a little harder. This is selected from an AMC12 problem, 2015B, problem 25. However, this is just a part of the entire problem. The entire problem is actually a lot harder, so we're just going to focus on the series part of that problem. So you see, this thing over here, it can be defined if we treat every part of the summation as a term, like this, then AI is equal to I plus 1 times x to the ith power. Or if you start from a1, you would arrive at this. Right? It's the same thing. How then are we to find a value for this? We again need a constant value, either a constant sum or a constant difference. And really, I don't see a clear way to find a constant sum here because the power for everything is different. So when you add two things together, they just doesn't match. How then are we to do it with a constant difference? Well, drawing from the inspiration from the geometric sequence, we can try. For simplicity, we'll be using this representation here, okay? So since s is this, we can let x times s be equal to I equals 1 to n, and now the formula is simply I times x to the ith power. So x minus 1s is equal to the difference of these two big things. Can we find a constant difference here somehow? Well, sometimes looking at these summation symbols, it's just not really easy to understand what is going on, so let's expand them a little bit. Well, basically we have this, and now we are going to take away these, and the last term would be this. So if you focus on each row again, and this time the row is a little bit tilted, but it looks more or less like that, we would find that it is actually simply this expression. And here, you see, we kind of gain something constant, because this is a geometric sequence which we already know how to find. That means even though it is not technically constant, because there's a variable in it, but we successfully made the coefficients constant and easy to deal with. So now this part can be represented as n x to the nth power minus 1 over x minus 1. And now, if we just replace it with this, then we're done. Because in the end, we just have to take another step and move this thing to the denominator of this expression. And then we officially have found the closed form for this series. And you see, this basically means that constant difference doesn't have to be truly constant. It's just something that you know how to solve by a closed form. And what is a closed form? A closed form refers to when you can represent an, which is a sequence, or sn, which is a series. Generally, we use these two symbols. If you can represent any of these only with n, without n and the first term, or the first few defining terms of the sequence, then it is called a closed form. So, for instance, you cannot use an minus 1 or n minus 2 to represent an. You can only use a0, a1, a2, or the first few initiating terms that define the sequence. This is called a closed form. So if we have anything that we can gain that already has a closed form, it essentially can be treated as something constant. And now let's test our skills again on another constant difference problem. This one is a little bit difficult because it requires a lot of creativity, but let's see if you can do this, okay? First try for yourself. And since I really want you to experience the process of problem solving while watching the video, you will have a chance to accept hints and then try to solve again. So first try to solve independently, then I will give hints. So the first hint, in case you're stuck, is that guess the power of this expression. If we have a closed form in the end, which degree would it have? If you guessed it is to the third degree, you're correct. So now we can work with third degrees because we know s is something to a third degree. Can you find something by examining the third degree equations and yield a second degree term? Is that possible? Well, perhaps you're stuck, but let me give you another hint. Consider two separate things that are consecutive, that is to the third degree. What can you gain from here? Can you somehow remove the third degree only to leave terms with second degree or less, so that you can represent the thing using second degree or less? Well, this time probably you have some luck, because you put a difference symbol here, and you gain the conclusion that after expanding this is 3k squared plus 3k plus 1. Well, great. Now, can you somehow turn this little term over here to this? Well, since we know since we already have this equation, we can manipulate it a bit by removing this 3k plus 1 part, putting it to the left, and dividing the entire thing by 3, so we have k squared. This is a really fancy way of representing k squared. Now sum this. S equals the sum of I equals 1 to n of I squared. And this is simply and let's just put the 3 here to the left first because it is a bit clearer. Actually, a lot of these are already known because if we first analyze this part, we know that this is actually equal to 3 times I equals 1 to n of I. And this is an arithmetic formula, arithmetic series. And the sum for this thing over here is 3 times n plus 1 divided by 2. And remember, we also have a plus 1 term, and the plus 1 term here actually is simply n because it is plus n times. So this renewed thing is actually equal to 3 over 2 times n plus 1, and minus n again. This part, however, looks scary, but is actually very simple, because if we expand this by writing it in a more intuitive way, this is actually simply 2 squared plus 2 cubed plus 3 cubed plus etc. plus n plus 1 cubed minus 1 cubed minus 2 cubed minus 3 cubed minus n cubed. So this thing over here actually is just n plus 1 cubed minus 1. And that is f. So if you're interested, you can simplify this further to something that is easier to remember, which is this. You can do the calculations yourself. And then we're done. So this thing, again, looks a lot harder, and I agree, this is not as intuitive as the arithmetic formula or the geometric formula. But then this is also an important technique that is actually very inspiring, because you first tried to guess what the series looks like, and that is actually an important step as well. In today's homework, you will also derive the third degree powers, which is going to be a little harder, but it's actually exactly the same thing. And by now, we have done dealing with series. And as a quick recap, dealing with series essentially requires constant values, because constant values are the key thing that you can convert from something unknown to something of a closed form. Now let's move on to sequences. And this time, we will be trying to predict what a certain value in the sequence is. First, let's try to model a word problem to a sequence. So we know there is a pair of newly born rabbits at the very beginning. So we have one pair here. This is the very beginning. Starting from the second month of birth, each pair gives birth to one new pair every month. How many pairs of rabbits are there in month n? Well, after the second month, a new pair was born. And that means there's pair 2. So at the third month, there's pair 3. At the fourth month, there is pair 4. In the meantime, pair 2 is going to give birth to the first pair of its own. And if we repeat the process, on month 5, the 6th pair is going to be born by the first pair, the second pair is going to give birth to the 6th pair, and the third pair is going to give birth to the 7th pair. And this process can be repeated. As you can see, this population is growing pretty fast, because essentially, every month, suppose there are AN rabbits at month n. Well, every month, it consists of AN minus 1, which is the number of rabbits that already existed before month n, and also the number of rabbits that were added at month n. And that is exactly the number of rabbits that existed at month n minus 2, because only those rabbits can give birth to a new rabbit. So this is the famous Fibonacci sequence. And this is basically the most basic linear recurrence. A linear recurrence is defined by Fn is equal to C1 times Fn minus 1, plus C2 times Fn minus 2, plus etc., plus Ck to Fn minus k. Of course, this is not a series because there are only certain terms concerned, from the last term to a few terms before that. This is the linear recurrence. And as you can notice, this thing is growing exponentially. For instance, let's list a few terms in the Fibonacci sequence. Now, after we list this out, we notice that this thing is growing exponentially. Since an is equal to the sum of the two last terms, this thing is greater than an minus 2 plus an minus 2, because an minus 1 is greater than an minus 2, which is 2 times an minus 2. So this thing is growing exponentially, because every single time this thing resembles a geometric sequence. So we can guess that an can be written as r to the nth power, right? This makes a lot of sense. Since we guessed this, and we know the recurring formula is an equals an minus 1 plus an minus 2, that means Rn is equal to Rn minus 1 plus Rn minus 2. As you can see, we can divide the entire thing by Rn minus 2, divide by Rn minus 2. We get r squared is equal to r plus 1, or r squared minus r minus 1 is equal to 0. Solving this, we have r equals 1 plus or minus square root of 5 divided by 2, where r1 is 1 plus 5 over 2, r2 is 1 minus square root of 5 over 2, and these are the two solutions. But of course, if we square this guy is not going to be very much a whole number, nor is it going to be a whole number when we move it up. So what happened here? We know that if we plug r1, r2 back into the equation, it is going to work. So for instance, let r equals 1 plus square root of 5 divided by 2. And this thing, if we just define an is equal to this to the nth degree, this is going to work. This is going to satisfy the recurrence formula. However, the thing wrong here is we actually have the definition a1 is equal to 1 and a2 is equal to 1. So the real conflicting thing here is that this thing is actually not satisfying the initial values defined. So we have to manipulate this thing somehow so that it satisfies. Well, how then? Well, before we dive deeper into the roots we gain over here, we will have to note something very important about a linear recurrence. Suppose Fn and Gn are both linear recurrences that satisfies this definition. Then, since Fn is equal to Fn minus 1 plus Fn minus 2, Gn is equal to Gn minus 1 plus Gn minus 2, then that means Fn plus Gn is equal to Fn minus 1 plus Gn minus 1 plus Fn minus 2 plus Gn minus 2. That means Fn plus Gn also satisfies this definition. So suppose Fn is equal to this, and Gn is equal to the power of the second root. Actually, let's first provide a stronger constraint, okay? Suppose we multiply these by a different weight. Let a times Fn plus b times Gn, a times Fn minus 1, b, a, b. And this thing still holds true. So a times Fn plus b times Gn is actually still satisfying this recurrence. So what I mentioned at first is just when a equals b equals 1, right? So that means, suppose we have some two weights over here, alpha times Fn plus beta times Gn. This is an, because one such weight must satisfy an. Otherwise, you cannot construct another sequence that satisfies an, assuming an is of exponential growth. Then that means, since we already know a1 is 1 and a2 is also 1, or a2 is 2, depending on what the initial values are, in this case, let's apply an easier way, okay? Because we will be trying to solve this thing, so we really want it to be as simple as possible. So let a0 be 0, a1 be 1, because this is one such possible Fibonacci definition. And meantime, it is the most reasonable, because at month 0 there are 0 rabbits, month 1 there are 1 rabbit. So we have the system of equations a times f0 plus beta times g0 is equal to 0, alpha times f1 plus beta times g1 is equal to 0. We know exactly these values, so we can solve for alpha and beta. In fact, alpha is negative 1 over square root of 5, beta is positive 1 over square root of 5. So that means our ultimate conclusion, we'll write this in yellow, a rare color, is that an is in fact equal to this, and we're done. This is a crazy solve. We have successfully represented a closed formula for an, and this is a huge formula. However, notice that this thing can be done on basically every single possible linear recurrence. So that is the power of this method, and this method is called the characteristic equation method. It is essentially guessing that this thing is of the form r to the nth power, solving it and then plugging it back in. And also we're utilizing the fact that linear recurrences have this nice little property over here. Otherwise, it cannot be done. So unfortunately, other recurrences of higher degree or other crazy forms, something like this, very crazy, this cannot be solved using a characteristic equation technique. And any such sequences that is more complex requires your observation to solve. So this is actually from the sample in the first video. Now, actually, the characteristic equation technique is a lot more advanced compared to what we already have, which happens when there are repeated roots. It is very, very annoying. For instance, problem 8 over here. If we apply the same thing, we're going to arrive at the characteristic equation that looks like this. We know this solves to R1 equals R2 equals 1. Then there's a problem because alpha times 1 to the nth degree plus beta to the 1th nth degree is always alpha plus beta, and this cannot possibly satisfy everything here. So we come across a problem. Well, I gave a very, very clear explanation of this in the materials down below in the description. So you can check it out if you're interested, but if you're not, don't worry, this won't ever happen in AMC12 because it is way too complicated. But actually, I think you can understand this, so check out the document below. Essentially, it's just trying to add more information to the only root we already have. Check it out. It's very interesting. And of course, if you want me to explain this on video in the future, just ask me below in the comment section. When I finish the AMC12 courses, I will be doing some freestyle videos that are just for math enthusiasts. So I might make a video about double roots or repeated roots in the future. So before we skip to too complicated stuff, let's first do a practice problem. This is 2024B problem 18 from AMC12. Difficulty 3. We have the definition of the Fibonacci formula, and we're asked this. So let Gn be equal to f2n divided by fn. We observe that Gn is equal to Gn minus 1 plus Gn minus 2. These are the key hints. And now try to solve it yourself, because remember to use the characteristic formula. Well, now let's apply the characteristic equation technique. And here, notice that G1 is equal to 1, G2 is equal to 3. So these are the initiating values. Then by applying this, we use the characteristic equation. So Gn is actually just a very clean form. Therefore, the first 10 terms are simply 1, 3, 4, 7, 11, 18, 29, 47, 76, and 123. Just sum them up, and we are done. The answer is 319. The reason that I just directly told you that this is a key observation is because the true way to solve this problem, in my opinion, is not the characteristic formula. If I require you to solve it in this technique, it might be a difficulty 4. In reality, I think the fastest way to solve this problem is just to calculate the first 20 terms of the Fibonacci sequence and just add them up. Because after all, in the end, we are still forced to add them up, and it is not easy to calculate at all. Okay, so it's just a demonstration because this is not truly the best way to solve it. So yeah, there is a much better problem in AMC12 that is much more closely related to the characteristic equation, but we cannot do it yet because it is related with number theory. In the future, we might try the problem. So by now, we have covered the second part of this lesson. A quick sneak peek on what problems we have today. So basically, sequences, we learned about linear recurrences and the characteristic equation. Now, following the natural path of exploration, we are now to talk about convergence. First, convergence requires a definition. Suppose we claim that a sequence converges at L. There is a nice way to visualize this. This is L, and a sequence just moves like this, gets infinitely close, but never passes over L. This is AN. Of course, AN is discrete, so essentially it's just points like this. But then the points, they kind of trace a path. So in the end, no matter how far AN gets, it still stays below this L. Of course, convergence can also look like this, or it can look like this. Anything like that is okay. So the more accurate definition, algebraically, is suppose the converging value is L, and we have any arbitrary positive number, epsilon. The claim here is for every possible epsilon, there exists an n, such that AN minus L's absolute difference, just the distance between them, is less than epsilon. This is hard to imagine, but it's essentially claiming that no matter how small the difference from L is, there always exists one such AN that can fit inside, and N can grow infinitely large. Well, there are some more common terms to describe convergence. For instance, monotonous. This example here, this is monotonous. This is also monotonous, which means either every term is larger than the last term, or either every term is less than the last term. And whenever we can say that a monotonous sequence stays below or above a value, of course, to stay below, it means the original sequence must be growing monotonously. And if it stays below a certain value always, then it must be convergent because it is bounded. It is not growing infinitely. However, on the other hand, if it is growing infinitely, that means for any m, there is a value greater. There exists an n such that an is greater than m. It is blowing off to infinity. A simple example of diverging to infinity is simply an equals n. Because for any m, just let n equals m plus 1. And we have a value greater than that, and it is diverging to infinity. So now it's high time we analyze something. This is called the harmonic series. So it is just the reciprocal of all the natural numbers. This thing looks convergent because it grows very, very slowly, because every next term added is growing smaller. So it feels like it's going to stop growing at some point. But actually, it is not the case. Given this information, try to prove that. We can do this by grouping. The groups are like this. For each group, we can change all the numbers to the power of 2 corresponding to that group. Then in each group, the value becomes 1/2. So essentially, this thing is just adding 1/2 over and over again, and this must be diverging to infinity. Try to prove this. This thing surprisingly converges, and try to again use grouping to prove that it actually converges. Well, in this case, we group like this, which is less than 1 plus a sum of 1/4 and a sum of 1/16, which is equal to 1 plus 1/2 plus 1/4, etc. Now this thing is convergent because it is always less than 2. Or to be exact, when it reaches infinity, it is exactly equal to 2. Because this thing over here is simply a geometric series. And by plugging in the formula, we know it is 2. Of course, here is an important warning that does not really have a relationship with AMC12. If you cannot prove a series is convergent first, you cannot assign a value to it. So that means even if we know the geometric series formula, we cannot apply it directly before proving that it is always less than or equal to 2. And, well, it can be done very easily, visually, because every single time, suppose this is the total length of 2, every time we just cut 1/2 of it, so cutting cannot ever get beyond 2. So we can first prove it is convergent and prove it is exactly equal to 2 when it reaches infinity. This is an example of monotonously growing but bounded series. So in case you're really interested in what this value is, this is pi squared divided by 6. And a quick note on future possible videos, I have discovered a way to prove this using geometry that even a middle schooler can understand. So if you're interested, tell me below in the comment section, I'll make a video about it. And more generally, we have this series, or sometimes it's called a P series. When p is greater than 1, it converges. When p is equal to 1 or less than 1, it diverges, as seen in problem 9 and 10. When it converges, this is actually the Riemann Zeta function, or it can be denoted as something that looks like this. I don't really know how to draw it. It just looks really ugly when I draw it, but this is simply this. The reason that for p is lesser or equal to 1, that we cannot define it like this is because, as I mentioned, if a series is not convergent in the first place, you cannot assign it a value. It is very important to keep in mind. So the final problem for today is this one, a difficulty 4 problem that requires a little bit of contemplation. Try it yourself first, and I'm going to give some hints to guide you through. So I hope the first thing you did is trying a few terms. Well, you notice that the first few terms is simply this. And if you have some superb pattern recognition skills, this is n squared plus 1 over n, or m plus 1 over n. You can plug this thing in and justify it. Therefore, since we're interested in an squared, this is simply equal to n squared plus 1 over n squared plus 2. So the sum of them is equal to the sum of n squared plus the sum of 1 over n squared plus 200. The first thing applying the formula we derived previously is 338350, a huge number. And this is 200. So now we're really just focusing on this guy. And we know this guy is between 1 and 2, from previous analysis. So the answer is simply 338551, because this is the greatest integer less than or equal to this. It cannot be 338552, because even if this thing blows off to infinity, even if we reach infinity for n, it is still less than 2. And we are done. So this is basically our lesson. We have reviewed everything about sequences and series that you will encounter in AMC12. Don't forget to check the notes below in the description, because I really think they're really important and some of the extra stuff is really helpful. And meantime, I would like you to prove everything you have learned today independently and then do the homework. This is the first homework problem, which I already mentioned. You're to derive a formula for this one. And then you will try to solve some series problems using constant sum or constant difference. Find a closed form for this, and finally this. These three problems are really similar. The techniques are similar as well, but they're all very creative. And also, in case you have gained the answer, you want to know if it is correct or not, because I don't have the answers in the materials down below, you can send them in at the comment section and I will check them. And then finally, we are to prove that the convergence and divergence of the past three series. You're to prove whether it converges or diverges. That's all. I hope by now you have a complete understanding of sequences, series, and convergence. You're ready to engage in some advanced math like the p-series and the Riemann zeta function. If you're not, don't worry. First do AMC12, you will learn a lot, and then after that, we will enjoy math together. So see you 2 days later in another video. Bye.